Yep. Thank you very much, Professor Adorovich. Needless to say that it is a very particular day for me, 19 years after I visited for the first time the kgh-kongres, to be with you. So it's very nice to have been for the 50th Congress here, and it's very honoring for me to have chairing the session Petar Novak, Marija Todorovic, and Sandro. The paper I would like to discuss with you today deals a bit with the hybrid photovoltaics and thermal systems for residential buildings. And we have to be aware that we are living really in a very interesting transitional period. This year in May, for the first time ever since Queen Victoria was still ruling the wave, the United Kingdom survived for a week and then for another 2 weeks without coal. So keeping in mind that this was the birthplace of the Industrial Revolution, it's quite interesting, and it gives us a clear sign of the fact that the times are changing. This is clearly mirrored, and I think that you should be quite aware of the figures that the European environmental and energy policy is based strongly on improving energy efficiency and increasing the renewable energy sources share in the energy balances of the country members, aiming at something close to 27–28% of energy efficiency by 2030, which is quite ambitious, keeping in mind that we are still in, that we are already in 2020 in reality. Having said this, this presupposes that we will have to do a lot of work additional to what we have been doing so far in the building sector, which consumes, roughly speaking, 40% of the energy in the EU. A quarter of the energy goes to households, and another 13–15% goes to the tertiary sector. And so I can be very happy in telling you that things are going well. Buildings have become much more energy efficient, and this is true, because if you think about how the energy consumption has developed, the specific energy consumption, kilowatt hours per square meters, in the last 20–30 years, miracles have happened. But on the other hand, in absolute figures, we consume more energy than we did a decade ago or 20 years ago. And this is for the very plain reason that we live in bigger buildings and we have more square meters per capita. So we have improved our efficiency, but we have increased our overall consumption. And this goes in particular for cooling. So it is clearly a sign that we have to focus in dealing with cooling energy as well. It is in this line of approach that we have to think about the nearly zero energy building. I cannot agree more with Professor Novak that it is a very interesting topic if it should be a zero energy, zero emissions, zero energy costs or whatsoever of a building. And it's also quite interesting, I think it was mentioned in the presentation by Maya Zoltan before, that there is a broad range of what a zero energy building is within the European Union. So it varies from 30 or 40 kilowatt hours per square meter in Croatia or in Malta to 160 in Austria for the residential buildings, and respectively for the non-residential buildings. And it includes various things from space heating and cooling, hot water, perhaps lighting, perhaps not lighting, installations, auxiliary forms, and so on and so forth. But at least there is a common framework and there is a common obligation. So independently of the fact that it is subject to debate whether one should strive for zero energy emissions, zero energy source or whatsoever, the strategy that we have to adopt to achieve the goal is the same. We need buildings that have a reduced demand, i.e. thermal insulation, high quality glazing, sun protection. We need passive and low energy cooling. We need highly efficient HVAC systems, whatever this may be, and we need renewables. And this is where it's starting to get interesting, because in the urban environment, utilizing biomass in the urban environment can indeed be quite tricky. Solar systems are more or less the ideal candidate. And you can have solar thermal systems, you can have photovoltaics, or you can have a bit of both. Because as I'm quite sure that everyone's aware, photovoltaics have a couple of nasty habits. They have an efficiency that decreases with increasing air temperature. So the idea of cooling the photovoltaic and utilizing the heat whilst at the same time increasing the efficiency of the photovoltaic cannot be very bad at all. And this is the idea behind PVTs. They have been in the market now for some years. They have been in the research for more than 20 years. And so the idea is that one could achieve the best of both worlds and utilize space. And there are hybrid systems that are being cooled by air, so by air collectors, solar air collectors, that are being cooled by water, so you have a PV and a solar water collector on its backside, and some even you have some evaporative form of collectors on the backside, which is probably the most extravagant systems you can find, but they are still quite interesting. And you can have many variations. You can have the water flowing above the PV, below the PV, in between, or whatsoever. It doesn't really matter. Any option would work. Every option has its pro and its con. As long as it works, we can discuss it. But why should we do this? We should go for a hybrid system, obviously, because we want to improve the PV's efficiency, because electricity is the more expensive energy form. So if we can increase electricity generation, we are happy. At the same time, we can utilize the heat, and we can utilize it, especially in summer, if we can utilize it in summer, regeneration is the magic word, then we have an overall very increased energy efficiency. Obviously, this leads to lower greenhouse gases emission and to reduced carbon footprints. Obviously, also nothing comes for free. It's a system that is expensive. It's a system that has a higher damage of risk. For those of you who are working on the solar branch, the danger of stagnation is always a problem for any solar system. If you have a hybrid system, it's an even higher danger. And depending on the type of the PV, for certain medium to high temperatures, you can have a varying curve of the efficiency. The million-dollar question is if the higher efficiency justifies the higher cost and the complexity. And the answer can only be given by quantifying the problem and trying to see if the total area of roof allocated to solar systems can be better utilized if we have, let's say, an area of solar and an area of PVs instead of having the sole area of PV, because that's the main concept behind it. And in theory, at least, this could be the case. But this is a very nice thermodynamic exercise for a PhD student. What is really important, in my humble opinion, is the fact that if we want to move towards zero energy buildings and beyond to plus energy buildings, we have to realize that the available surface on the building's envelope is a commodity in short supply. And this applies to single-family house, as you can see it on the right hand of the slide, where you have a single-family house in Cyprus. You can't have more sunshine in Europe than you have in Cyprus, but even the roof of a single-family house hardly is enough to accommodate PVs and thermal systems enough to cover a big part of the building's demand. And if we speak of high-rise buildings, which have also to be zero-energy ones, then it starts to getting really critical, because you don't have enough space unless you go to really advanced options like semi-transparent PVs, or perhaps ground source heat exchangers if you have a suitable soil or whatsoever. But on a high-rise building, the roof is almost non-existent with respect to the embedded volume and what you have to cope with. So you need to utilize every square meter available. So one can go for, let's say, typical polycrystallic silicium photovoltaics with air or with water flowing behind and some sort of collector. And these are just some curves that indicate how the efficiency is improving. There's a typical efficiency curve of any solar system. And if you add a water collector, or if you add an air collector from behind, you can have an increase in efficiency, which is perhaps at the order of magnitude of 5 to 15% for the electricity production, which is not bad. And you can utilize a big part of this heat. So the next question is, does it work? Well, let's consider a couple of case studies. I have to admit those are calculations and not measured values, but these will be available hopefully soon. So let's take a typical single or two families house of 200 square meters and examine it for Athens, Thessaloniki, and Heraklion. Athens is a very typical Mediterranean climate. Heraklion is really close to Cyprus. Thessaloniki is more or less like you have in Split, since we have Sandro on the panel. And those would be the heating and cooling loads for the three locations. And the typical characteristic of the Mediterranean building is that you require both heating and both cooling, which is what makes our life a bit more complicated, but at the same time a bit more interesting. So if I use 30 square meters of a hybrid PVT system with a water one, let's speak of Athens, then I could have on the top part a solar fraction, that is from 25% in December to almost 100% after April. And this could be achieved with a PVT system almost as good as with a conventional system. The almost as good means a difference of about 5 to 10 percentile units, which may not sound a lot, but in reality it means that you have an increase in the efficiency of the electrical part, of the electrical component, by 20%, 22%. For the gentleman before asked about the electricity, mentioned about the energy prices. For an electricity price of, roughly speaking, 18 cents per kilowatt hour, it makes a difference. You lose something in the thermal system compared to a purely thermal system, but the overall balance is not bad. And if one would think about increasing the surface in order to increase the solar fraction, then the answer would be clearly no. This is a problem that we face in all renewables and solar systems in particular. You have to balance, on the one hand, the maximization of the solar fraction, on the other hand, the maximization of the utilization factor of the system. So it wouldn't make much more sense than to go, let's say, above 30 square meters or 15 square meters per residence, and this would be close to the values that everyone who has worked with solar systems knows that are reasonable. The other example is a bit more tricky because it tells you a bit about the difficulty of working in the urban environment. Take a typical office building somewhere in the downtown part of any city. This is in Thessaloniki in that case. A building that is pretty old. It has been partly refurbished and it's quite reasonably protected. 1,000 square meters of air-conditioned areas with reasonable heating and cooling requirements, but with a very small available roof due to the shape and the obstacles and everything else. So you won't get anything more than 60 or 70 square meters of solar systems, be it thermal or PVs. So what could you do, or what could someone do to make this building a nearly zero energy one, since we have to refurbish it in one way or another? The one option would be to try to fit solar systems on the roof. 60 square meters of photovoltaics will barely be enough to cover 50% of the, or 80% of the electricity, no percent of the thermal energy. You could utilize thermal systems, forget the electrical part, which in an office building is a disaster, or this, which was the suggestion of an architect in our group, one could try to utilize the shadings on the roof with vertical or horizontal fins, the shading fins, which would be in reality photovoltaics. Okay, and utilize the roof for thermal systems. I mean, the design is for free, the implementation is a bit expensive. So, playing with this figure, you could end up with something like 200 square meters of photovoltaics in the east, 50 in the west, and 150 in the southwest option, so 400 square meters of PVs. But since they are rather unsuitably located on the vertical facade, even if they are moving and with different azimuths, don't expect miracles. So if you go for such a complicated option, which would be the conventional wisdom to make the building a nearly zero energy one, you end up producing, let's say, 63,000 kilowatt hours per year in the best case, which would be 65 of the building's electrical demand, nothing left over for the space heating. If you put another 40 square meters of solar collectors on the roof, you may pick up 40 to 50% of the heating load, nothing for the cooling load unless you go for solar absorption. Now, what would be the other option? The other option would be to utilize the 70 square meters for hybrid PVTs. And this gives you the huge advantage that you can place them at the ideal azimuth and the ideal inclination. So with those humble 65 to 70 square meters, you can have a 20% higher PV increase compared to the 400 meters put on the louvers. And you can have also some 26,000 kilowatt hours of thermal energy, which would mean something close to 20% of the building's heating load and another 20% of the building's cooling load. So it's not nearly zero, but it's as much as you can get. In addition, as a mechanical engineer, I'm not really happy of having PVs instead of fins rotating daily following the sun. They will not last for long. I'm not really a fan of small tracking PV systems. But of course, if one would consider the currently known market prices, it would be something like 30% more expensive than the conventional approach in the best case. And to be also fair, we do not have long-term experience with hybrid PVs about their aging. So this would also be an issue which has to be still determined. In other words, and so I think I will also have compensated some of the time used up by Professor Novak, I think that if we want to move, or since we have to move towards zero energy buildings, there is a limit to what can be done in reducing energy demand, and especially in existing buildings, this limit is quite high. We cannot affect the building's orientation. It is too expensive to have a major refurbishment of the building envelope, and we cannot change its use, or as long as its use not changes, we don't have options to intervene with its operational patterns. Therefore, we have to make do with the little space available in the urban environment, and this applies to residential and to non-residential buildings, and we have to utilize this little space in order to make the best out of it, in order to have the biggest yield of renewables. Hybrid solar systems have the huge advantage that they increase the efficiency of the electric part of the PVs when it is most wanted, and that is in summer. So you can have your high efficiency heat pump being driven by electricity produced by the high efficiency PV, because otherwise you can have the conventional PVs, but with 40 degrees air temperature, its efficiency will certainly not be something to be proud of. The second big advantage is that you have that is allow you to have the best possible utilization of precious space, and space is really something which there's never enough of it, especially in the urban environment. Finally, hybrid systems make a smooth distribution of thermal output, which is quite interesting if you want to cover, if you have to cover heating and cooling demands, of course, provided you have the respective heat distribution systems, but that's another story. What remains to be addressed is the matter of feasibility and the matter of duration over time. Both parameters affect the investment's feasibility over time, and both parameters are those that will, at the end of the day, determine the choice made by the developers. What we cannot afford to do is to stick to the, let's say, traditional energy systems as we have been using them over the last 30 or 40 years in the building sector, because I think it has been more than enough proven that we have reached the limit of the evolution of those systems. Now there is a time for some sort of a quantum leap. Thank you very much for your attention.